think we should start because let me see problems for today. So we have to prove that, yeah, this one, for example, the probability of the open interval a and b is f of b if f of b minus f of a. Yeah, because the first one we did it already, I think. So who? No? Okay. Huh? Again? The first one? It should be, yeah. So you have something like this in your test, so I recommend you to understand what is going on here. So look, let's look at the definition. Let's use, yeah, so the probability that, again, we have A, we have B. So do you understand what is written here? No. What exactly do you understand? F, B, B minus, or B minus? Okay. This is the value of the function from the left, right? So if you have a function, I don't know, like this, this is f, this is b, then here we have b minus from the left, and here we have b plus on the right. Okay. Now f is the CDF, p is just the probability, right? So this is the probability from minus infinity. So here, of course, a is less than b, right? So the probability of this ab, we have to take the probability from minus infinity to b minus the probability of minus infinity to a. So this is the probability from minus infinity to b open, right? Minus the probability from minus infinity to a close or open. Close, right? Yeah, and this is the CDF. So from here we can see that this, what is this? So f of what? F of a. So we have the first one. Okay. Here we have minus. That's okay. And here we have, this is not f of b because here we have opened, right? Okay.
So therefore, it cannot be f of b because it's open. Therefore, by going from the drawing right there, it's f of b minus.
Yes, but exactly.
But is it enough of a proof? Because I tried it as well, but is it enough?
Of course, why not? So let's look at this again. I mean, we already did this, but let's repeat it. So look, this is what? This is the, so here we have b, right, b. So let's take some sequence from the left, which converges to b. For example, b minus 1 over n, right? So xn is a sequence that converges from the left to b. For example, xn is just b minus 1 over n, right? We have that n is bigger and bigger, so we have that this is closer and closer to b, right? So, and we need, and what do we need? And we need the union of all of that. right? So we need the union from n1 to infinity of minus infinity to b minus 1 over n close. So the union of all these sets give us this is equal to this open interval. And here we have close, right? So this is clear, this part, yes? Okay. So here we have the probability, right? But what next? What is next? So this is equal to what? Sure, but why? I mean, there's some step missing. Which one? And then this is the most important step, like this one. So there's a property that we prove. No, that's not true. We didn't prove it. There's a property of the probability that we call continuity, right? Continuity. Sorry. Hard, huh? And it means, it says that if we have the countable union, this is equal to the limit from of n tending to infinity of the probability of each of these sets minus infinity to b minus 1 over n. Because of this property. Continue. Like that? Yes? Okay. Because of this property. All right? So you need to know this property. And this is very important. This is highly important, this property. We didn't study this property previous semester. So be aware of that. So from this union, we get the limit. And also if, and this is true, by the way, because this is a sequence of sets which is increasing. So this is a increasing sequence of sets. So because we have this b minus 1, for example, then we have b minus 1 over 2, then b minus 1 over 3, and so on. So this is bigger and bigger and bigger and bigger. So this is an increasing sequence of sets. And the limit of an increasing sequence of sets is the union. Okay? And so the union is the limit. So we write the limit here. And because of this property, the limit can go out. So we put the limit out. And we know that this this is the CDF of this point. So we have that the limit when n tends to infinity of the CDF on this point is, of course, f b minus. Left. Left, right? So that's it. So here we obtain this over here.
This is a bit tougher than past homework. Past homework is question that you can visualize it. This one is
Yeah, past one, I mean, everything that we did previous semester is probability theory for engineers. You are not engineers. You are computer scientists. And you need to know all of this, right?
So can I change to be a engineer?
So probability theory is very interesting because you can know probability theory in very different levels, like calculus, right? You can know just that the integral from a to b of a function, this is the derivative, right, of on b minus this, right? all of these things, this is for engineers. But
in real life situation, I can think of distribution, yes. But when I think of this, like, I don't know.
let me show you where do we apply this. We have some CDF. And this is the point A. This is a CDF, and this is the point A, so we have the discontinuity on this point. So what is the probability that psi equals A? So this is we have the CDF of a random variable psi. Is this distance. This distance is the probability that psi equals A. Why? Because the probability of some fixed x is f of A from the left, sorry, f of A from the right minus f of A from the left. So look, we don't need to write from the right because this is continuous from the right. F of A minus f of A minus. So this minus this. So this distance is this probability. Now prove it, right? And we prove it like this. Okay. We have to find, we can solve this one so that it's clear. Okay. So look, again. The probability of some fixed x, so let's call this x, right, is, what is this? Oh, here, the probability of what is that? Is the probability from minus infinity to A close minus the probability from minus infinity to A open. It is true or not? So we are taking out, from this set, we are taking out this set. What is left? Sorry, A, x, right, x, x. So we have the set, the close, right, from, and we take out the open set. So we are left only with x. So this is clear? No, with x. We have the set, okay, from minus infinity to 2. So this minus infinity to 2. This is equal to just 2, right? And we know that this is f of x, right? But this is not f of x because this is open. But we did already all of this, and we obtained that this is f of x minus, right? So that is why if, for example, in this point, y, in the point y, f of y, sorry, f of y is equal to f of y from the left, right? That is why this is 0. That is why the probability of getting y is 0. So everything should hold here. So if we have the CDF and there's some point in which the function is continuous, then the probability of getting this fixed point is 0. But if we have something like this, so it's not continuous here, then the probability is this distance, right? And we prove it over here. Look. So that is why if we know the CDF of a function, we can easily find the probability that psi is equal to some a using the CDF of this function. Yeah. By the way, so I told you that we have absolutely continuous probability distributions, and we have discrete distributions. But not only those distributions, but every probability distribution is a combination of these distributions. For example, like this. Maybe we have the following CDF. This is a CDF. Is it discrete? Is it continuous? No, it's not absolutely continuous, it's not discrete. Here, so here, and here is absolutely continuous. And here is discrete. It's a combination of both, yes. Yes. So I think I have an example here. Let's post. So this is the following CDF. This is not absolutely continuous. This is not discrete. This is a combination of both. Why? Because in 0, before 0, we have 0. Then, look, when we have 0, here's 200. When we have 0, it becomes something else. It becomes 30 over 2 over 200, right? So this is some point here, right? And then we get another point here, which one? 150 over 200. And then we have here 1, right? No, it's not. So here, from here we have 120. Right? So for example, if we want to find the probability that this random variable is greater or equal than, I don't know, 100, then we have to look at the sum of this plus, so here we use the probability density function, and here we use the probability mass function, right? Good. Great. Now let's continue. So is this clear for you? Yeah? You will get it, don't worry. Now, so, and you can prove all the others from the first exercise exactly in the same way. Now, second exercise. we have the discrete distribution, Poisson, and geometric, right?
For the first question, did you mean to find all the things? Or what do you mean by
Yes.
all the
Yeah, the even positive integers. So what do we have? We have the Poisson distribution. So again, this is what? X over x factorial e to the minus lambda. Right? And we need to find the probability of all such numbers, of all even integers. So these are two, right? Number 2.
Oh, no.
Somebody, please.
I can try the third one.
The third one, really?
I have an idea.
Okay. Gabriel, can you hear me? All right. So what's the difficult part here?
I don't know. That was a bit. I didn't have an idea.
Okay, let's think about this one. So what is this set? Let's think about this set. I think that you guys care because of how this set is written. This is 2, 4, 5, and so on, right? 2, 4, no, from 2. 6, 8, and so on. Right? So we need to find the probability of this set. So let's find the probability of this set. Yeah. Since they don't intersect all the elements here, then this is just the sum of the probabilities. What is the probability that we get 2? Probability that we get 4. Right? What is the probability that we get 2? It is Poisson. Yes. Okay, so what should I write? Yeah, lambda is just lambda.
Gonna be lambda to the power over
Right? Plus yeah. So we have to sum up our all even numbers. Lambda to the x, e to the minus lambda, and x factorial. And this is the answer, right? So this is going to be the answer. So now we have to find this. How do we find that? Look, what is this? So e to the lambda is what? Is the sum from x 0 or 1? Yeah, 0 to n of lambda to the x and x factorial. This is true, right? Sorry, to infinite. Why this is true? Because this is, so the sum from 0 to infinite is 1. So it means that, so if this is 1, this sum, sorry, this is 1, it means that the sum is going to be e to the lambda, because e to the lambda times e to the minus lambda is 1. So this is e to the lambda. Yes, so look, the sum from x0 to infinite of lambda to the x e to the minus lambda and x factorial, this is 1, right? This is like the same that we said about the density, probability density function, that the integral from minus infinity to plus infinity is 1. This is the same. So the sum over all possible x is 1. If this is 1 and this number is fixed, so this is some number, this is a constant. So this doesn't change. So we can put this out. This is e to the minus lambda. So it means that this sum should be equal to e to the lambda. Because e to the lambda times e to the minus lambda give us 1. Just like that. So that's the logic that you have to use. So we know this. And we can, and we know that e to the minus lambda, e to the minus lambda is just the sum right, like this. Just let me check. Yeah. So it's the same, but in this case we have lambda to the x factorial, and here we have minus 1 to the x. Okay? So we somehow know this. So what if we have this plus this? E to the lambda plus e to the minus lambda. So every time that x is an odd number, we have minus. So they cancel, right? So we are left with even numbers. So that's it. Right? So this is the sum over all the even numbers of lambda. Sorry. Yeah, lambda to the x factorial, and wait, but something is missing. What is missing? So we have this and plus this. Okay. 2 times. No, wait, what is? It should be enough. Just a minute. So all the even cancel times this. Link A. Okay, I don't see. There's some problem here. I think that this should be. All right. I see it. No, wait. This is for all. Okay, so we have e to the lambda. This is the sum. And we have this for even. So we are looking this sum. So we have to multiply. So the probability is going to be e to the minus lambda by this sum, and this sum is this e to the lambda plus e to the minus lambda. But I have something different here. Why? Just why 2? Okay, factorial. Ah, of course. Yes, of course. So this 2 is missing here because if k is odd, then they cancel, right? So for example, there's 2 times. All right. This is the answer. By the way, here is from 0. You are right. Yeah, I mean 0 is possible for the Poisson distribution. So this is the answer. Is this clear? Yeah. No, it's not. Yeah. No. Okay. Now you have to do the same, but for the geometric distribution.
Not promise nothing.
Doesn't matter. Okay.
Let me just see the. I need to.
Let me show you. So look. So do you have any question by now? No? Yeah, this answer is amazing. Which one? How do we get this? What is the real what? This one. This is not a formula, this is a number. E to the minus lambda, and all of this. This is a number. Lambda is 5. So put 5, 5, 5, and 5, and this is a number. How do I know what? You can put whatever lambda you want. Lambda is any number greater than 0. So put, I don't know, I'm telling you 5. Right? Because we are talking about the Poisson distribution. When you talk about the Poisson distribution, you give lambda from the beginning. You say, okay, let's talk about the Poisson distribution with parameter 2. And then you can replace the lambda by 2 and you get this number. This is a number. Okay, fixed number. That's it. This is the probability. Right? Yeah.
Therefore, we can come to the realization.
Right. Y from -1.
Because you see, we can say x can be equal to 0.
In this case, x is not 0, by the way.
But in that case, here's going to be 1. Here it's going to be 2 minus 1 is going to be 4, it's going to be 3. Therefore, it's going to be equal to the sum from x being equal to 2 up until anything. 1 minus 2 x minus 1. So I think.
Yeah. So look, what do you have in common here? This.
Yes, we can take it out.
Yeah. So you can write p, y minus p, times what? Let's write this. 1 plus what?
P. And then it's going to be the geometry.
No, p, yp. No, y minus p, right? y minus p squared.
Oh yeah, of course. My bad. 1 minus p squared
Plus,
1 minus p. No,
4 to the 4.
4 to 1. It basically this one looks the same as 1 plus x squared plus x cubed, and it's geometrical progression.
And this is equal to what?
1?
No.
No, doesn't sound right. Well, it should be equal to.
In other words, so and don't forget about the geometric progression, right?
Maybe we should do this.
So look, 1 plus r squared plus r cubed. This is what? This is 1 minus 1 over 1 minus r.
Yes. Yeah.
Right? What is r in this case?
X
Squared.
X squared.
Right? So all of this is 1 minus x squared. So the answer is what?
So we can substitute it here, this sum.
Yeah.
And therefore, we're gonna get. We can take.
So it's p times y minus p.
You can take it out of the sum.
Yeah. So look, this sum is this.
Yeah.
So you write p.
Like this.
So let's write the answer here. Right here. So the answer is p times y minus p times what?
Times the sum.
Wait. Not the sum. The answer. Write the answer.
Oh. Okay. 1 minus x squared.
Yeah, but what? And x is what?
In our thing, x, if I'm mistaken, is 1 minus p.
Y minus p.
So this would be p 1 minus p multiplied by 1 minus 1 minus p.
Yes, that's it.
I think we can.
Yeah, we can of course do something about it, but
like this, whatever. Yeah, but this is the main.
yeah.
Can I
That's
try
it.
the next one as well?
Yes, please.
Try.
Wait, did you already write this? I mean, yeah. Are you right?
There's a recording system.
Yeah, well. Okay, do you understand what we have to do here? Yeah.
I'll try. Do all proper distribution hold identity of x plus y? Yeah, so I think we can think of the rules of the CDF here.
Okay. This. Look, we have this sum from here, this sum. This is equal to this. And we are taking out p times y minus p. So we have p times y minus p, and here we have 1 because we have p times y minus p. Okay, good.
So for this question, I think, I'm not sure if I tried, but I think we need to check the first one. So we have, just before I write this, we have the identity. I just
Indicator.
I just call it ternary. But in cx plus y greater than, so x plus y greater or equal to 0. So here is that if it is greater than 0, it's going to be 1. If it's not greater than 0, it's going to be 0, basically. Right. So the first part that we want to check is suppose we have this. So suppose that y is going to be a constant.
Wait, just a sec. But we haven't, we haven't talked about this because we have two random variables here. Let's. I don't know why I gave you this one. This is for the next class. Yeah, because we can do it right now, but we need. We haven't talked about the CDF of two random variables. Yeah, sorry. So this one for next class, okay? Yeah, because for this one we have to talk about not. So we've been talking about the distribution of a random variable of x, Now we have x and y, so we have something else. So this is for next class. I didn't get. No. Okay, so let's see what.
So can we think about it in a sense, like, so I think of, let's say, proving the first property of CDF here. Suppose that we have 2x plus y.
Yeah, it's, I mean, okay, let's do it. What is x plus y?
Well, I think like you can, what I thought is maybe we can break it into two parts. Maybe one is going to be constant to prove what happens if it tends to infinity with x and tends to infinity minus infinity with x.
Yeah, no, wait, let's do the next class because here we have to verify that the limit when x tends to infinity and also that the limit when y tends to infinity, and we haven't done that on the lecture. Okay, so next class. Great. So let me just see something here. Yeah. Now, we have a random variable, okay? We have some random variable xi. And please I need you to listen to me right now very carefully because this is not that easy. So we have a random variable, okay? And any function of a random variable, well, and some functions of a random variable is also a random variable. This is not that trivial. This is something that we need to make sure that this phi is a Borel function. I'm not going to talk about the Borel function right now, so just think about any function that you already know from calculus. So if you have that x is a random variable, then the x squared is also a random variable because a random variable is a function, right? And if you have a function of a function is a function, right? So I think this is clear. A function of a function is also a function. So a function of a random variable is also a random variable. Not always, but in most cases. Now, what if we want to find the, so, and we know the PDF of this, of xi, right? It's given, it's normal or something like that. Let's find the PDF, of phi of xi. Okay, so if we have a function, if we have a random variable, and we know that and we know the probability distribution of this, the density function of this random variable, we can find also the density function of any random variable being a function of something else. For example, if I am telling you xi has the uniform distribution between A and B, you already know that you know the PDF of this, right? And I'm telling you, okay, let's find the PDF of this function, xi squared, xi cubed, right? Or, I don't know, 2 xi plus 3, right? And this is something that you will have in your text, that's for sure, okay? So you need to get a function, you need to know how to get the density of a function of a random variable, okay? So how do we do that? Look, let's do it just, so let's say that, so by definition, let's find the CDF. So what is the CDF of this function? In the point y, let's use the point y, right? By definition, this is the probability that phi of xi is less or equal than y. By now, this is clear, right? Now, this is the probability that phi of xi is less or equal than y. And what is this equal to? Here, imagine that we have this and we have this. So we have xi here and we have phi of xi. Yes? Phi of xi is something like this, for example. And we need to look at the probability that phi of xi is less or equal than y. What is y is any point here on the line. So this is y, for example, y. So the probability that phi of psi is less or equal than y is the probability that psi is from here to here. Because here, look, in this interval, phi of psi is less or equal than y, right? So we need to look at the probability of this interval A. So the probability of this is equal to the probability that psi belongs to A, right? And what is the probability that psi belongs to A, for example, in this case? So this is the integral, because we know the density of psi. So this is the integral over all x such that phi of x is less or equal than y, right? So this x from here, this x from here, this is this set. So the integral over all this x from here and the density function of psi. T. But and this is the CDF. But here in this case we have that phi of psi is any function. Now what if we have that phi is an increasing function? So again, in this case we have something like this. This is phi of psi. This is psi here. It's increasing, right? So strictly increasing. Strictly increasing continuous function. I will explain why do we need all of this. So again, here we have some y. And what do we have here? Phi of the minus 1 of y. Yes? The preimage of this y. So the probability that phi of psi is less or equal than y is the probability that psi is less or equal than this, right? So this is equal. So in this case, am I right? In this case, this is the probability that psi is less or equal than y to the minus of y, right? But we are talking about the inverse function of this, right? And we know that the inverse function of a function exists if it continues and strictly decreasing or increasing. That is why phi has to be a strictly increasing continuous function. If it's not, then this is not possible. All right? So try to remember that I told you that the probability theory is actually calculus. Okay, so in which case do we have that a function is has an, how do we call it, in the inversion, I forgot. How do we call this function? The inverse function, right? So in which case a function has an inverse, right? In the case when this function is strictly continuous, is strictly increasing, or continuous, strictly decreasing. Okay, and this is something that you know from calculus. You already know all of this. This is so easy for you. So that is why we need this function to be like this. Okay. Now we have this, but on the other hand, if we have that psi, that phi is strictly continuous, strictly decreasing, continuous function, so it's something like this, right? So here we have y, phi of minus 1 of y. Now, what is the probability that phi of psi is less or equal than y? What should I write here? Who tell me this gets 0.5 points in your exam? What should I write here?
In this case, the unit probability psi less or equal to delta y.
Delta? Which delta? We don't have any delta here.
Like the thing, like the
Phi, right? Right? This is phi, no? No. No. You don't want an excellent grade. I can see that. Well, he wants an excellent grade. Greater, right? Not less or equal. In this case, has to be less or equal. In this case, it has to be greater because look, the function is less or equal than y if psi is greater than this. Plus 0.5. Okay, you can get maximum 1.5 points in the lectures, so you still have 0.5 to go. All right, so look, we have two cases. Case number one. Oh wait, no. In case number two, psi is less or equal than this, psi is greater or equal than this. And what is this by definition? Yes, the CDF. No. F of what? Of yeah. On this point, right? And here. No. Well, if we have less or equal and we have greater or equal here.
Minus.
1 minus.
1 minus.
1 minus, yes. Because this is less or equal, this is greater than equal, so 1 minus less or equal give us all the possibles. Greater or equal. Okay, so look, we have some F here, CDF, and we started with this. So we started with this. We have a CDF here, we have a CDF here, and we have a CDF here. What do we need to get? We need to find the density. And we know that the CDF is continuous. So it's differentiable. So we can find the derivative, and this will give us the density. Then from here, dy of f phi psi y this is equal to the so the d of dy of f of this is psi here, by the way, right? Psi psi 1 y. So let's find that. So here we have, this is just the density of phi of psi y. This is what we're looking for, right? So we need to look at the derivative of this. What is this? So this is the derivative of the CDF is just so this is the CDF of, so now the PDF of psi in this point, right? Times the derivative of the inverse of this function. So this is, and what is this is equal to? First semester calculus. What is the derivative of the inverse of a function? Hmm?
1 point. This one, 1 point.
So you remember?
I can try. Not get on try. Yeah, 1 point.
So this is xi in this point over 5 xi in this point. This is the answer. Okay, could you tell me the answer for this one then? So if phi is decreasing, it's just minus. What is the derivative of this? What is the difference? There's one difference.
It's just 1 minus.
No, what is the derivative of 1? Okay, so why 1 minus? Minus. So plus, if this is what, plus if we have increasing phi, and minus if we have decreasing. So in this way you can find the density of the function of a random variable. All right, let's finish.